Great. Okay, so hello everyone. Thanks for coming along to the AFMS seminar for this week. It's my pleasure to introduce our speaker, Dr. Edward Hinton. So Edward is a Harcourt Dodge Research Fellow at the University of Melbourne, and he completed his PhD at the University of Cambridge, and he's also held a London Mathematical Society Research Fellowship at the University of Bristol. So Edward uses low order models, numerical methods, and also lab experiments a little bit maybe to give insight into the underlying physics in different fluid systems. So please take it away, Edward. Thanks.
Thanks, Kat. So today I'm going to talk about some gravity current models in heterogeneous porous media. So this is work I've done during my PhD and following my PhD with Andy Woods, Andrew Hogg, and Herbert Huppert at Cambridge and Bristol. So gravity currents in porous media have been well modeled by lots of people, and this has sort of been a really growing field in recent times because of the interest in carbon dioxide storage. And so here are some plots from some seismic images from Sleipner, which is a carbon dioxide storage site in the North Sea. And so carbon dioxide is captured from, it's often captured from natural gas that's extracted. And then it's re-injected underground to sort of prevent the emissions associated with that carbon dioxide being released into the atmosphere. And it's injected into porous layers. And this seismic image shows the kind of layering that goes on. And the CO2 is injected down here at P, and then it comes up and it hits these baffles of low permeability shale, and then it spreads around them and drains through them. And there's been a lot of interest in kind of how these images can be interpreted to try and understand how fast the CO2 is spreading, how fast it's leaking, and to try and understand the permeability of the rock. Because all these things kind of help us understand the safety and the security of the particular storage project in question. And because this is quite a sort of emerging technology, there's sort of a lot of demand to show to regulators and the public that this can be safe and an effective way of storing CO2. And so this just shows one way of modeling this kind of system is injecting CO2 at the bottom, and then it sort of fills up beneath a low permeability layer and drains through, and so on and so forth as you go through all the different layers. But models have also been used to try and understand how to invert the seismic data. And it's been shown that kind of through just a simple model of CO2 being injected into a uniform layer, that you can get non-uniqueness in the sort of inversion problem of how much CO2 you've injected and the permeability from your seismic, because you don't have enough detail to capture the kind of low viscosity finger at the end. Models can also be used to try and understand kind of the trapping mechanisms of CO2. So CO2 will dissolve in the ambient brine, as you see in these images. And it can also be trapped in the pore spaces as it's displaced by the ambient brine. And both those mechanisms reduce the quantity of mobile CO2. And so it's sort of interesting to try and understand how quickly that happens and what controls the rate at which the sort of the volume of mobile CO2 decreases in time. But most of those models have focused on uniform porous media because it's kind of the simplest way you can model a rock. But if you look at many rocks at all, you notice that they really are not uniform. You get all sorts of different types of heterogeneity in the typical sandstones that are porous and are typical sites for CO2 injection. So here you can see that you get kind of discrete jumps in the structure of the rock, in the kind of grain size. You can get inclusions which are very different permeability. You get layering. So this is from Mona Vale Beach in New South Wales. And you get these very fine layers that are sort of deposited by geological currents, could be deposited by turbidity currents. And this produces the layering you see here, these cliffs in Dorset as well, where you can have low permeability layers, high permeability layers spaced out. And also even within a single layer, you can get a strong gradient in permeability. Another cause of heterogeneity in the rocks is many of the sites for CO2 storage were sites that were previously used for hydrocarbon extraction, because if it's a porous rock, and we know quite a bit about the geology, it makes it quite a promising site to store carbon dioxide. And that means that you're going to have abandoned wells that may be poorly plugged or impermeable. And so the CO2 is going to interact with those abandoned wells and may leak through them or may go around them. And so it's sort of another aspect of the heterogeneity of the rock that has to be captured in a model. And so today I'll talk about two types of heterogeneity. The first is a sort of inclusion of different permeability in just a migration of flow in a porous media. And the second is a vertical gradient of permeability. So the first model to consider is just when you have sort of flow on an inclined porous plane. It's driven by gravity down the slope. And you've got a porous medium and an inclusion in the middle of different permeability. And the question is, how does that perturb the flow of the fluid in the porous medium? And so we'll neglect the ambient fluid and just consider the injected fluid here. And so in a CO2 sequestration case, this would be upside down and you have flow up the hill and it'd be underneath the impermeable plane, but we'll just consider it on top for the moment. So it's inclined at an angle beta. And we'll consider kind of constant flux of fluid from the top. And in 3 dimensions, if you look at this from above, you've got a plane and then you've got a cylindrical inclusion, which will take as having radius L, and the flow is going down the hill and it's interacting. It can go around or through this cylinder. So to model this, we'll use Darcy's law, which is just to say that the flux is proportional to the pressure gradient. We have a constant of proportionality. We use a shallow approximation, which is that the velocities perpendicular to the plane are much smaller than the velocities in the kind of parallel direction to the plane. So it's flows mainly in the downslope direction. And we'll consider the steady state that's attained once this flow has passed the cylinder and there's a kind of a constant flow thickness profile as the fluid flows around and through the cylinder. And so it's been shown that you get away from the cylinder just for constant flux, steady flow over an inclined plane, you get a constant flow thickness and a constant velocity given by this H infinity, where phi is the porosity, mu is the viscosity, q is the flux, k naught is the permeability, and beta is the slope angle. And you can then calculate the u, which is the sort of velocity, and it's a function of the permeability, and then you get the sine beta term, which is the sort of component of gravity acting down the hill. And then you get these cos beta dh dx and dh dy terms, which are the kind of components of gravity acting into the slope. And they act to smooth out the kind of any perturbations in the flow depth. And so we're just considering permeability, which has a discrete jump between the interior and the exterior of the cylinder. So we'll non-dimensionalize the system by just scaling the quantities with the obvious things. We'll scale the thicknesses with the far field flow thickness that arises from the steady state, and we'll scale the sort of in-plane coordinates with the radius of the cylinder so that dimensionlessly it has unit radius. So the flux can then be written like this, where K of R is the dimensionless permeability, which is 1 in the exterior, and lambda in the interior, where lambda is the permeability ratio. And you have this parameter F, which is the sort of ratio of the length scales in the problem. It's the ratio of the upstream flow thickness to the cylinder radius. And at the cylinder boundary, you have continuity in the flow thickness and continuity of the flux. And then you can take the divergence of the flux in steady state just to get this very simple nonlinear advection diffusion type equation for the flow thickness H in steady state. And obviously the boundary condition that the flow thickness must return to 1 far away to its unperturbed steady state. And it's not too difficult to solve that system numerically using a finite element package. And here are some kind of flow thickness profiles in the steady state for the case of large F, which is when the cylinder is very narrow relative to the thickness of the flow. And so the flow is going from left to right, and you're just looking here at y is positive, So because the problem is symmetric about the center line, we just need to worry about the top half. And this is lambda is 3, so the cylinder is 3 times as permeable as the exterior. And what happens is that the flow comes in, and it is sort of drawn in and then accumulates at the downstream boundary. And so you get an increase in flow thickness at the downstream boundary and a decrease at the upstream boundary. Similarly, if you consider a narrow cylinder that's less permeable, so lambda is 0.3, then the flow is diverted slightly around the cylinder. So you get an increase in flow depth upstream as it sort of builds up, and then a decrease downstream. And if you look, these are the kind of flow paths, the streamlines, and you see that indeed for this case where it's more permeable, you draw in fluid from the exterior, you sort of focus the flow, and you divert the flow slightly for a less permeable cylinder. And we can interpret this behavior by just doing some simple asymptotic analysis. So we say, well, these plots suggest that the flow thickness is approximately 1 everywhere, which sort of makes sense because if it's a narrow inclusion relative to the thickness of the flow, you think that it's not going to perturb the flow depth very much. So you just write h as 1 plus 1 on f times a function h1, because we're in the regime where f is large. And then it turns out that h1 just satisfies Laplace's equation with the sort of flux boundary conditions at the boundary of the cylinder. And you get this solution here, which is anti-symmetric, which is good because this sort of profile does look anti-symmetric. And interestingly, this is the exact same profile you get for pressure-driven flow in 2 dimensions past a cylindrical inclusion. And so it's sort of the solution you get for potential flow in a Healy-Shore cell, or potential flow where you sort of have a constriction in a Healy-Shore cell. And so the reason for this behavior is that the H1, the perturbation to the flow depth, is really just the kind of analogous to the pressure perturbation in the potential flow problem. And the other interesting thing here is that H1, the perturbation is quite small, but a small perturbation in the pressure can lead to quite large divergences in the flux, because you saw in those previous slides that you were pulling in flux, you're focusing flux from quite a large region, even though there's only a small perturbation to the flow thickness. And you can compare this result along the center line, and it shows reasonable agreement with the numerical results. And you can also go to second order, which requires a matched asymptotic expansion, and that shows even better agreement with the numerical results. Okay, so then in the other regime, which is probably more interesting because it's sort of more novel, is considering a very wide inclusion relative to the flow thickness that's coming on. And it turns out that there are 3 different regimes depending on the permeability of the inclusion. So if the cylinder has similar permeability to the exterior, then all that happens is that the flow thickness is 1 upstream, and then it comes into the cylinder. And in the cylinder, the flow thickness must adjust because if f is small, because it's a very wide cylinder, these dH dx's are basically negligible because f is small. And so the flux is basically just the permeability times the flow thickness. And as the permeability changes, so the flow thickness must change to account for the constant flux. And so you really just get constant thickness, but they're different because of the change in permeability. And then you get a slight boundary layer where the flow thickness adjusts from its constant thickness upstream to its constant thickness in the cylinder. You get a boundary layer upstream and downstream as it comes out. And then there's sort of this slight perturbation in the flow thickness downstream because of these boundary layers, which I'll come on to talk about more. So this is quite a simple regime. Everything's just controlled by the variation in permeability. And you can zoom in on those boundary layers using some asymptotic analysis to capture the flow thickness, and then you can compare it to the flow thickness predicted numerically, and it works quite well and it captures the behavior. As the flow thickness is 1 and then a half because the permeability doubles and then returns to 1 downstream. And in this case, if we kind of calculate numerically the flux plot here, then you can see that there's basically no diversion of the flow. It diverts slightly in the boundary layer, but really it doesn't change at all. It just speeds up and slows down as you go through the inclusion. And so this is quite different to the case of a narrow cylinder where there was focusing, because now if you have your cylinder as higher or lower permeability, because it's so wide, it can't actually focus or divert the flow. Okay, but there's a sort of caveat to that, which is when the cylinder becomes, the inclusion becomes a very low permeability, that boundary layer starts to become very large. So you can see here, even for just lambda is 3/4, so for a slightly less permeable cylinder, because the flow thickness has got to increase in the cylinder, you get this quite significant jump in flow thickness at the upstream boundary. And as that grows, as the permeability of the cylinder reduces, that can start to drive its own flow. And what happens, so this is for a 10 times less permeable cylinder, is that eventually that boundary layer drives the flow around in the tangential direction around the cylinder. And so there becomes more flow around the cylinder than there is flow into the cylinder. And we can use some simple sort of flux balance arguments to try and understand what exactly is going on in this diversion regime. So to do that, we'll just consider first an impermeable cylinder, and then go back to consider the sort of low permeability case after that. So for an impermeable cylinder, the flow comes down with constant thickness, and then it must form a sort of a horizontal pond, because there can't be any flux into the cylinder, and so it sort of forms this stagnant pond upstream of the cylinder. And then in the stagnant pond, the flux comes in, and there must be a tangential flux around the cylinder to remove the fluid that's coming into this stagnant pond. And so we can take the radial flux in the pond, so that's the flux into the cylinder, and say, well, that must be 0 because it's a impermeable boundary. And that gives us an expression for the flow thickness in this pond, where the flow is almost stagnant. And then we can calculate just by balancing the flux into the pond with the flux out, just by integrating h times the tangential velocity, which is just going to be sine theta because we're in the small f regime, to attain what this function g of theta is. And we just get it goes like f to the minus a half. And so if we consider rotating this to the sort of flat coordinate system for the flow thickness, then we see that here's the numerical solution for lambda is 0, that straight line, and compared to this pond solution, and you can see it sort of captures it pretty well near the upstream boundary of the cylinder along the center line. And then if you consider low permeability cylinders, they show reasonable agreement with this, showing that there's sort of similar physics going on. Now for an impermeable cylinder then, we find that the maximum thickness goes like √2 f to the minus a half for small f. And from our previous narrow analysis for large f, we found that the maximum thickness goes like 1 + 1 on f. And you can find an empirical expression for the flow thickness, for the maximum flow thickness, that agrees with these two regimes in the small f and large f limits. And that's given here, it's 1 + 2 on f to the half. And if you compare that to the numerically calculated maximum flow thickness, it actually agrees for all values of f to within 2%. And so although the asymptotic analysis applies for small f and large f, you can use what that tells you about some of the quantities to predict sort of universal rule of thumbs for how the flow thickness can behave. Okay, so returning to the low permeability cylinder again, if we take this pond solution and we say, well, if the cylinder is very low but not impermeable, very low permeability but not impermeable, then the flow thickness must be continuous. And so the flux into the cylinder from this pond is given by the flux just on the inside of the cylinder. And so we know the flow thickness is there is continuous, so we can just obtain it from the outside. And then the flux is just given by k times h, because we can neglect these f terms. And so the radial flux into the cylinder is just lambda h cos theta integrated over the boundary. And that goes like lambda f to the minus a half. And so we can then say, well, for this sort of low permeability regime where the flow is predominantly diverted around the cylinder rather than going through the cylinder, that must be much smaller than 1. So lambda must be much smaller than the square root of f. And so when you get this, when the inclusion behaves as impermeable, depends on its permeability as well as its flow thickness, as well as its width relative to the thickness of the oncoming flow. Because if you imagine a very wide cylinder, you need it to be of much lower permeability for it to totally divert the flow. Okay, then you get the third and final regime, which is of a very high permeability inclusion. And so in this case, it's the boundary layer at the downstream boundary that becomes important. And it's slightly different to the low permeability analysis, because what happens is that the flow from upstream comes into the cylinder, the flow thickness changes. So this is for lambda is 100, it's 100 times more permeable. The flow thickness decreases by a factor of 100 to maintain the flux within the cylinder. But then once it gets to the downstream boundary, it can't get out, essentially, because this exterior of the cylinder is of so much lower permeability than the interior. And so it gets diverted by the cylinder boundary into this pond region at the kind of focusing point at the downstream point of the cylinder. And so we're going to use similar ideas, but they're slightly different, to try and capture what's going on and the physics of this behavior. So in the region in which there's sort of negligible flux out of the cylinder and it's being diverted in the tangential direction, we write that the solution is just given by another pond because there's zero radial flux, where m of theta is to be determined. And again, we balance the flux in with the flux along the sort of in the tangential direction. And that gives you this expression for m of theta, which is that it must go by like lambda times f to the minus a half, and then it depends on theta. And theta is measured as 0 in the positive x direction, and it's measured increasing in that direction. And so for theta near pi by 2, or away at least from theta is 0, this shows good agreement with this is the dot dashed line, m of theta, with the flow thickness along the cylinder boundary. And for this regime to be accurate, we need negligible flow out of the cylinder in this sort of region, which means that lambda f to the minus a half must be small, which means that lambda must be much bigger than 1 on f. And so that's a slightly different relationship as for the low permeability cylinder, because you're getting this focusing and then they'll be draining out of the cylinder through this region here. Whereas for the low permeability cylinder, there was no flow sort of across the boundary. And so it led to a different type of behavior. Okay, so then you get a second pond region, which is much deeper near this focusing point. So the flow is focused by the first pond, and then it accumulates here, and it is balanced. The flux from the sort of tangential flux is balanced with radial flux out of the cylinder in that region. So we know that there can't be any theta dependence then of this pond at the sort of downstream point, and so we just can write the flow thickness like this because it must be stagnant. So that's just a stagnant pond, and then it's a balance of the flux out, which is just h times cos theta, again using the continuity of the flow thickness across the boundary, and we compare that to the flux in from the tangential solution, which is just going to be unity, because that's the flux that comes into the cylinder. And we can obtain a prediction for this x0 and a prediction for the maximum flow thickness. And it goes like f to the minus a third. And that here is compared to the flow thickness along the downstream boundary, and it shows pretty good agreement. So in summary then, for a wide inclusion, there are 3 regimes. If you have fairly similar permeabilities or a very wide inclusion, you get that the flow essentially just goes straight through the cylinder. If the cylinder is of relatively low permeability, you can get diversion predominantly of flow around with a little bit of draining into the cylinder. And if the cylinder is of very high permeability, you get flow coming in, and then it gets diverted at the downstream boundary to this sort of focusing point, and it drains out of there. And what's interesting is that this high permeability cylinder doesn't actually focus any flow until you get to the downstream boundary. The upstream flow is not perturbed at all by the high permeability cylinder. And so these kind of simple ideas around flux balance arguments and the diversion of the flow can be applied to any shape you like. You can apply it to, for example, a square cylinder. And so this is a low permeability square cylinder, and you get the same kind of behavior, that you get a deep region accumulating, and this is a pond, and you can balance the fluxes to again see what's going on there. But interestingly, for a square cylinder, you don't get a deep region forming at the downstream boundary when it's a very high permeability. And that's because you can't have the focusing at the downstream boundary that you did for a circle, because this downstream boundary is perpendicular to the flow direction. So no matter how high permeability the square cylinder is, the flow just goes straight through. And so this cylinder is very high permeability, but it doesn't do any focusing at all. It just goes straight through, and you get a flow thickness change. Okay, so that concludes the kind of first problem of looking at how heterogeneity affects these models. And then the second related problem is to consider flow in a confined layer where you have a vertical variation in permeability. And so in these kind of porous rocks, you get permeable and impermeable layers, and within the permeable layers, you can have significant variations in permeability. So this is from a tracer test. This is the hydraulic conductivity with depth. And you can see that the kind of conductivity varies by an order of magnitude over just a few meters. Within this is one sort of flow unit. And so we want to try and kind of understand to the leading order, how does that affect the flow? And here is a permeability profile from a sandstone from the North Sea. This is from a log from a core. And you can see that the porosity doesn't change that much within each layer, but the permeability, this is on a log scale. So the permeability, there are quite strong gradients in the permeability with depth. So to model this, we take one layer of this kind of layered sandstone system, and say it's a permeable layer separated by two impermeable layers. And we inject CO2, which is relatively buoyant in comparison to the ambient brine in the system. We say we inject the fluid at a constant rate. It has lesser density and different viscosity, and we're going to be interested in how does the interface between the two fluids evolve. And the novel feature is that we're going to allow the permeability to vary across the layer, but we'll keep the porosity constant. You could include a varying porosity, but it doesn't really change very much. And again, we'll just use Darcy's law. It's going to be in the shallow regime, because once this layer becomes flooded, once it's filled by the input fluid, the velocity is predominantly in the x direction, and the velocities in the y direction are small by comparison. And we'll neglect any mixing between the two fluids at the interface between them. So there will be intermingling between the two fluids, but there are quite a few experiments that have shown that that can kind of be neglected at leading order. And so we'll assume this interface is sharp between the two fluids. Okay, and you can use mass conservation to derive sort of the governing equation for the evolution of the flow thickness, H of x and t. And here it is, it's phi dH dt, where phi is the porosity, Q naught is the input flux, and you get this term here, which is associated with the kind of injection driving flow down the layer, along the layer, and you get this term on the right-hand side, which is associated with hydrostatic pressure gradients, and that smooths out the interface, and it's proportional to this U, which is the characteristic buoyancy velocity, and that's the velocity that a parcel of the less dense fluid would move with, would rise with in the more dense fluid if you just released a little parcel of it. And we also have the viscosity ratio appearing between the two fluids. And if this was a uniform layer, you'd replace this K0 of H just by H, because K0 is the depth integrated permeability. Okay, well, it's sort of for reference useful to consider what happens in a uniform confined layer. Now, this was studied by Pegler and a few others 6 or 7 years ago, and they showed that if the input fluid is more viscous in a uniform aquifer, then you essentially just get a plug flow at late times. The injected fluid fills the layer, and the interface just moves at a constant velocity downstream. It's quite simple. If you have a less viscous input fluid, then you sort of get a Saffman-Taylor type instability. Because the input fluid is less viscous, you get this single finger forming, and this finger moves along in time. And you get one finger forming because you have buoyancy kind of suppressing the formation of other fingers which would arise owing to the sort of instability of the input of one less viscous fluid. If you didn't have buoyancy, you would have lots of fingers. And then for equally viscous fluids, you get sort of a singular behavior between the two regimes, where you get that the interface moves downstream with constant velocity and spreads out with its extent growing like the square root of time. Now, if you then, so these shapes for this sort of low viscosity input can be calculated quite simply by just saying, well, at late times, the interface has become long. And the role of buoyancy is purely to ensure that it's occupying the top of the aquifer. And so you can neglect this second order term and just get a first order PDE, which you can solve using the method of characteristics. And it just gives you the velocity at every height. And that gives you these dashed lines for the evolution of the flow thickness. And you can use exactly the same idea with a gradient of permeability in your layer once you've incorporated it in your model. And so here I'm just comparing the sort of traveling shapes, because in that characteristic solution, everything just moves with x going like time, so that's everything sort of the velocity varies with the flow depth. And if the permeability is higher at the top of the layer, you get your viscous finger traveling further because it's traveling faster at the top, as compared to this case here of a uniform permeability. And kind of unsurprisingly, if the permeability is lower at the top of the layer, then your low viscous input fluid, the interface is shortened and more concentrated. And so these are all for a viscosity ratio of 1 to 10. And so you're sort of suppressing your viscous instability in this case by both buoyancy, ensuring that you don't get viscous fingering elsewhere, and this permeability gradient slowing the velocity near the top of the aquifer. And in fact, you get a slight shock here because the characteristic solution gives you a turning point. If you insist that the input fluid can't underride the ambient fluid because the input fluid is buoyant relative to the ambient fluid, then you have to introduce a shock. Now, if you injected fluid very quickly and imagine that the sort of middle of the aquifer was of much higher permeability than the top and bottom, then you can imagine that you would violate that condition and you'd get a fast finger forming in the middle. But we'll assume that the sort of fluid is injected slow enough that the kind of buoyancy equilibrium is maintained. And there's some interesting work that's been done experimentally and numerically on how kind of significant buoyancy needs to be in comparison to the injection velocity, the injection flux, in order for this equilibrium to be maintained so that you get a monotonic interface shape. But we'll just assume that's the case. And you can also a problem in CO2 storage is that you bypass a lot of the rock, because if you inject your CO2 is typically much less viscous than your ambient fluid, then it will shoot along the top of the aquifer in this viscous finger. And if this is sort of the box that you have put CO2 into, you've only accessed 6% of the space in this case. And so it's not very economical to drill a well and then not be able to access a lot of the rock that you could access. And so a uniform layer, you get a bit more in, you get 10% accessed, and here you're getting much more of the layer accessed because it's a much more concentrated profile. And so it sort of suggests that if you are selecting a location, you might want to select locations where the permeability is higher at the top of the aquifer, because the CO2 is going to run less far for the same amount that's injected. And so you can both store more CO2, and because it runs less far, you're less likely for the CO2 to reach fractures where it might migrate into more shallower layers or even to the surface. Okay, so that kind of shock where you have a fixed extent region and a growing region occurs in two kind of modes. You can have the case where your input fluid is of relatively low viscosity, as in the case here, but the permeability is low at the top. So for a low viscosity input, you would get in a uniform aquifer a growing kind of viscous finger, but the low permeability at the top sort of suppresses that, and you get a mixture of a growing region and a fixed region. But you can also have it when you have a more viscous input, but you have a high permeability at the top. So the more viscous input wants to just flow as a plug flow, but because it's faster at the top, you get a sort of competition. And so you get a fixed extent, constant velocity region and a region that grows in time. So we can sort of sum up all of these behaviors by considering a regime diagram. So here's your viscosity ratio, M. So M is less than 1 is a less viscous input fluid. And on the x-axis is your permeability structure. So delta K is 0 is a uniform layer. Delta K is positive means you have the permeability increasing towards the bottom. And delta K is negative means you have high permeability at the top of the layer. So this is just for a linear permeability structure. In a uniform layer, what you find is that you have this sort of singular regime here, this cross where you have the root T interface growth. And then for a more viscous input, you have the shock. For a less viscous input, you have this growing type behavior. And then if you consider permeability that's higher at the top of the layer, then it can flow faster. And so you're more likely to get the kind of viscous finger than you are other regimes. And so it can occur even for viscosity ratios larger than 1. But conversely, if you have permeability lower at the top of the layer, then you're not going to have this regime because you've suppressed the viscous finger, and instead you're going to get sort of shocks or fixed extent regions. And then 2 and 2' are the two modes I previously discussed for the kind of case where you have a fixed extent region and a growing region. And then 3 is where you just have a plug flow with just a shock. There it is. And you can apply this idea of this characteristic solution to any permeability profile you like. So here I've done it for nonlinear permeabilities, and you can consider kind of a low permeability lens lying above a high permeability lens, and look at the kind of shapes that you get. And again, having low permeability at the top of the aquifer leads to a greater proportion of the rock that you access. And if you take a typical layer and change only the permeability structure, and consider, if it's run 5 kilometers, how much CO2 have you gone into? You see there's a strong variation with the kind of CO2 that you get into that layer depending on the permeability structure. And you can also calculate the percentage of the rock that you've accessed in each case. And finally, in that problem, you can consider multiple layers. So you can calculate the proportion of the rock that's accessed as a function of the permeability gradient, the sort of storage efficiency. And you can say, well, what if you're injecting simultaneously from a line well into lots of different layers, and you don't know the permeability in the layers, but you can say with some confidence that there's some probability distribution of the permeability structure in each layer? Then you can use our simple calculations for the storage efficiency as a function of the permeability structure, and some probability density function for each for the permeability in each layer. So you get all these different profiles to calculate the probability density function for the total storage efficiency of the system consisting of all these different layers, which are separated by impermeable layers. And so you can calculate this for sort of any number of layers you like and see what happens. Okay. This model also has kind of uses for interpreting where individual parcels of fluid go. And so if you consider releasing a tracer into the CO2, so this, you may want to do this to track where the CO2 is going and to track whether it's leaking or to track the velocity. But also you might want to model how a tracer moves because you're interested in adding a surfactant or a viscosifier to try and change some of the properties so you get a more concentrated, shorter interface so you access more of the rock. And that's also important in hydrocarbon recovery, in enhanced oil extraction, but you want your kind of interface to be steeper. And it also is important to understand where individual fluid particles go if you're tracking contaminants in aquifers, or you're kind of trying to understand the reactions that are going on. And so the tracer migrates and it moves into this sort of growing finger, and then you could measure it at a downstream well. And so we're going to apply our results to try and understand how the tracers that are affected by the flow travel with the flow, what happens to them. And so again, we'll neglect any mixing with the ambient and assume that the tracer is only soluble in the CO2, in the injected fluid. So in a uniform aquifer with a less viscous input fluid, the tracer simply, if you release a line of tracer, it simply gets carried into the growing sort of solution, because this growing nose of the current is supplied continually by fluid from upstream, and so the tracer just travels further and further downstream into the growing nose. And so here it is, a sort of partitioning the fluid behind the tracer and the fluid ahead of the tracer. And it's simple using, in a uniform aquifer, you can use the calculations for the flow velocity to calculate that the distance from the head of the flow is root t, and the extent of the sort of nose grows like t. And using that expression for the velocity that you've calculated, you can show that an individual sort of parcel of tracer, its extent grows like root t because of the stretching owing to the growth of this nose, and its thickness goes like t to the minus a half, basically because of mass conservation, because it's got constant mass. And so this is slightly strange because there's no diffusion in this problem. It's a uniform aquifer, so there's no kind of pore scale or mechanical dispersion that we've included in the model. But the stretching of the nose, owing to that low viscosity finger, actually leads to stretching of the tracer that goes like root t. And so if you were measuring it downstream, you might think it was some kind of dispersion associated with molecular diffusion or pore scale dispersion. But actually, it's solely owing to the advection in the nose. So it's slightly odd behavior. You can then take the model with a vertical gradient of permeability and consider what happens when you also include diffusion. So upstream of the nose, if you just consider what's going on in the kind of case where it's the total aquifer, so it's kind of constant thickness, then you're going to get shear dispersion because you've got a gradient of permeability, and so the flow velocity varies with the flow thickness, with the depth, and you also have diffusion. So your profile of tracer gets sheared, and then you get large concentration gradients in the kind of cross flow direction. Those then get smoothed out by diffusion, and then you get enhanced shear dispersion or Taylor dispersion, and that leads to a kind of increase in the a long flow dispersion coefficient as compared to the uniform case, as you can see by the different scales in these two plots. So if you consider how that sort of interacts with the growing nose, well, here's the uniform case, and then if you have a vertical gradient of permeability, then it sort of is sheared over by the gradient of permeability, higher permeability at the top. It moves into the nose, and eventually the shear dispersion kind of gets, well, firstly, it becomes vertically homogenized by the gradients in the concentration being smoothed out by diffusion. And then the shear dispersion actually switches off, because as you go further into the layer, you access less and less of the permeability gradient. And so it behaves as a uniform aquifer. And so once you get kind of this tracer traveling far into this growing nose region, you can apply all the uniform results. And so again, you get that the extent of tracer grows like root t, t to the half, because of the stretching of the nose rather than diffusion or shear dispersion or anything to do with the permeability gradient, which is a bit surprising when you think about it a bit. Okay, so hopefully I've shown that you can kind of use these simple models to try and understand lots of different things about flows and porous media, and use them to try and inform kind of an understanding of the different physical processes going on. And you can, one of the nice things about these models is you can extend them to consider other aspects. So you can consider different geometries, you can consider inclined geometries, you can consider 3D axisymmetric geometries, and you can apply all the same ideas, and it's quite straightforward to do that. You could consider leakage from the layers. So in that case where you've got a porous medium, you could suppose that, you know, what if it's an abandoned well and there's leakage, and you could adapt all the results to provide bounds on how much fluid is leaking and how fast it's leaking, just by incorporating extra terms in the governing equations. And you can use the asymptotic results there. You can incorporate capillary effects. So a problem in flow and porous media is that when you have very low porosity, the fluid may not enter, may not invade the low porosity regions because it can't exceed, the pressure doesn't exceed the capillary entry pressure. And so you can incorporate capillary effects like that in these models. And you can also incorporate the fact that CO2 gets trapped when it's displaced by ambient brine rather than the CO2 displacing the ambient brine, because the CO2 is non-wetting. And so it gets trapped in the pore throats, and you can incorporate that. And you can also adapt these models to incorporate dissolution as well. Okay, so I'll conclude there and take any questions.
Fantastic. Thanks, Edward, for the talk. So we do have a little bit of time for questions. If you're in the audience and you want to ask a question, feel free to unmute your mic and go ahead. While people are having a bit of a think, I might ask, this is just a really quick question actually, Edward. So in terms of the timescales, like say a realistic timescale for the CO2 movement, like does that happen relatively fast? Like is this a matter of hours or days?
No. So if we go back to the cartoon, so kind of if you put an injection well here and then maybe another kind of measuring well, maybe 500 meters downstream, it might take 6 months to travel that kind of distance. So it's pretty slow. It's in a very kind of low Reynolds number regime. Yes.
Okay. Makes sense. And then I just had another question, which was to do with the multiple layer situation that you had. So you didn't spend much time on this, but I just wanted to, I didn't quite understand what's happening between the layers. Are you just adding, like, is there interaction between the layers?
So you could, so in this problem, I was just considering that the mean permeability in each layer is the same. But you allow the gradient of permeability to vary.
Okay.
And then you say there's no interaction between the layers.
Yep.
And it's totally impermeable. But you could also allow for different mean permeabilities across each layer, which would then kind of partition the flux in different ways. And so you could also add that to the model, because the higher mean permeability layers would get a greater proportion of the flux. And you could also consider kind of a small leakage, because if you have really high permeability here, then you're going to get leakage into this layer. So you could, there are sort of lots of different ways that you could adapt and extend these models.
Yeah, I guess there's lots of complications you can kind of just keep throwing in there if you wanted to.
Yeah.
Great, thank you. Okay, so in the audience, any questions? Cool. I think so far, no big questions from the audience. If I can take advantage of this and just ask one other question on the first half of the talk.
Sure.
So that was mainly, I think, entirely about steady state flows. Yeah. Is there much that you can do? Like, is that kind of a realistic case, I guess, or would you normally have to consider the evolution of these type of flows?
Yeah, that's a really good question. So in short, I think you can, so we did consider the transient evolution, and because you know what the kind of final steady state looks like, you can calculate a lot of useful quantities. So for instance, when you have a ponded region upstream, you know how much fluid is in that. And so you know how long it's going to take to get to that regime. And because you know the flux. And so you can sort of calculate when this occurs. But you can also do things like apply these arguments to transient cases, because if you know that the kind of cylinder is basically impermeable, then you can kind of just, same idea of balancing the flux in with the flux tangentially, and include a transient component, even if it's not kind of fully developed, that it's sort of high enough. So you can do a lot of things with the transient problem as well. It's just easiest to sort of first consider the steady state.
Yeah, no, definitely. It just occurred to me, like, okay, what happens if the flow speed changes quite quickly, and then you need like a new build up or eating away even of some of those layers.
Yeah, and there can be kind of hysteresis as well, because if you sort of really change the rate at which you inject, you could imagine that you may no longer be able to get fluid into your cylinder, and the kind of fluid in your cylinder is trapped because of the kind of capillary entry pressures. And so, yeah, they can be sort of quite interesting feedbacks.
Yeah, that would be a really interesting case, I think. Okay. Thank you. Thanks for answering my questions. Anyone from the audience? Last chance.
Oh, sorry, stop sharing.
Oh, that's okay. All right, I think otherwise we'll thank Edward once again for his talk and hopefully see you all next week at this time. Great, thanks.
Thanks.
Thank you.